Welcome to the University of Chicago video series on generative AI. I'm Kevin Boyd, the Chief Information Officer at the university, and I'm very pleased to welcome to our program today, Rebecca Willett.
Thank you. It's a real pleasure to be here, Kevin. Thanks for inviting me.
Thanks for joining us. So Rebecca is a professor of statistics and computer science at the University of Chicago, and today we're going to talk a little bit about the fundamentals of AI and machine learning. So, Becca, let me ask you, could you give us a little bit of an overview of artificial intelligence and machine learning, and maybe highlight for me how is it really significant in today's tech landscape?
Yeah, that's a great question. I think we're seeing some huge changes right now. Some of them are very visible. I think many people have already played around with ChatGPT for fun or even for, editing documents that they're writing, and have been amazed at some of its capabilities. And when we search for things like images on Google, and it can easily identify exactly the type of image we're searching for, we can attribute a lot of that success to AI technologies as well. But those are really just scratching the surface. We're seeing people use AI to help guide autonomous vehicles or self-driving cars. We're seeing AI being used for scientific discovery. So AlphaFold is an example of where people used AI to figure out how, proteins, these long sequences of amino acids, fold to form a configuration that's actually functional in our body. And then I think, we're exploring how AI can be used in all different kinds of contexts, in criminal justice, in business applications, in engineering, in medicine, and more. So it's got a lot of potential, and the pace of discovery is really phenomenal right now.
So as things are changing so rapidly, one of the questions I get asked often is, are there some core concepts that people should understand? Are there some basics that would help people understand what's really going on with generative AI?
Yeah. Well, so first let's just talk about AI and machine learning in general. Okay. And there, I think the key concept is that we're learning from data. And it's a lot like how a little kid learns something. When I was teaching my kids about the differences between cats and dogs, I would show them lots of picture books, and we'd look around at animals in the park or on the street. And I would also point out features like the size or the pointiness of the ears. And eventually they form kind of a mental model so that when they see a new animal, they can correctly identify it as a cat or a dog. And so with machine learning, we're doing something similar. We're presenting a machine with lots and lots of images of cats and dogs, and it is extracting features of those images, things analogous to size and ear pointiness, and figuring out how to, from those features, make a prediction about whether the animal is a cat or a dog. And that's a super simple example, but I think is sort of a core building block of how a lot of AI and machine learning works, where we're presenting it with just tons of examples and trying to use modern tools like neural networks to extract these models that lets them make good predictions or generate new examples.
So Becca, your last answer made me think a little bit about what we sometimes talk about with hallucination, where when we talk about cats and dogs, if we fed an image of a wolf, we might get an answer of dog. And that could be actually a data issue with how we train the model, right?
Absolutely right. If we're going to learn from data, then the data we feed in is super important. And so if I feed in 1 million pictures of cats and 1 million pictures of dogs and a single wolf, then I could imagine the computer saying, hey, if I never predict wolf, I'm still going to do pretty well most of the time. No one's going to get upset. But then that can cause real problems, right? And so we have to think very carefully about how we curate and select the data that we use to train these methods, and how the methods are going to be used, and how that should inform the way we form these data sets.
Interesting. Okay. So it seems like over the last couple years, we've been speaking mostly about generative AI, or at least it seems like in the public eye, that's what we're talking about over and over again. But can you help us understand a little bit about the difference between generative AI and the discriminative AI, which seemed like the predecessor to this?
Yeah, I think of discriminative AI as being more prediction oriented. Like I feed in an image and I want the AI system to tell me what type of animal it is or what is the content in that image. Or even, in the context of medicine, does this image contain cancerous cells or does it not? Whereas generative AI, I think more of as, creating new examples. So after feeding it, billions of images of dogs, I would like it to generate a new image of a dog. So they're just serving different purposes. But it turns out that a lot of the underlying mathematics and computational tools are very similar.
So that was interesting. Let me ask a little bit more about data. So can you talk a little bit about how we use data to create actionable insights with AI?
Yeah, that's a great question. I mean, data has really been the fuel guiding this renaissance. Before, for instance, in computer vision, we would maybe try to design algorithms that would take a picture and try to decide whether it was a picture of a chair or not by having a list of rules about what constituted a chair. And it took a lot of work to build that up and a lot of human insights. And that's just completely different than what we can do today in completely data-driven models after we fed these systems examples with millions and millions of different types of chairs of all shapes and sizes and colors. And so the first teams that built some of these data sets just revolutionized the field. And when we look at what OpenAI has done with ChatGPT, a huge part of the work that they've done is building up these huge data sets that allow us to extract meaningful knowledge from data and not rely on these more rule-based systems.
I think sometimes people don't really understand what we mean when we talk about training. And to hear you say that, the idea that we are sharing lots of images or lots of similar data to teach a model how to recognize patterns, essentially.
No, that's exactly right. And one of the most powerful and popular tools right now are neural networks. And I think when we see these at first in the media, they seem huge and intimidating because we hear there's like billions of parameters, but the core concepts are very simple. So earlier we were talking about like taking an image of a cat or a dog and figuring out what type it is based on size and pointiness. So mathematically, I could think about just computing a weighted sum of these two features and seeing if that weighted sum is above a threshold or below a threshold. And so then I use all my training data to figure out, well, what are those weights and what should that threshold be? So now I can think about that very simple building block as being sort of a core piece, and I can daisy chain a bunch of those together to form a much larger scale and more complex system. And this is what we would call a neural network. And so a lot of the effort in this space has been about, well, what is the right way to daisy chain this, and how do we make this scalable and tractable, and how do we decide how we construct the architecture of these networks in a way that's attuned to special applications, whether it's protein or images or text.
Okay, that's great. So that's a really helpful sort of mental model of what a neural network is. Now, you are a professor of statistics and computer science. Mm-hmm. So tell me a little bit more about how statistics plays into this. How do probability and statistics influence the models?
Yeah, I think that they play a critical role. I mean, one of the big challenges that we face today is not only making a good prediction, but assessing the uncertainty associated with that prediction, right? I mean, when we're talking about identifying cats versus dogs, the stakes are pretty low. But if we're talking about predicting whether somebody should be eligible for a loan or whether somebody may or may not have cancer, the costs of mistakes are high. And we would like to be able to say, hey, I'm 90% sure that this person has no cancer, as opposed to, maybe they don't have cancer, but it could go either way. And so this is where, this is the bread and butter of the statistics world, is trying to figure out how to take data and not only make predictions, but conduct inference to really say how much certainty we have associated with different predictions.
So related to that, we sometimes talk with AI about generalization. Can you talk a little bit more about what that is?
Yes. So this is really about how well my model, after I've used all this training data to train it, how well it's going to work on new data. So I not only want to make sure that my model did a good job on all the training data where I knew the truth, I want to make sure it's going to work in the wild. And so what we see in practice a lot of times is that we've got these carefully curated data sets where we've got a training set and then a separate test set, so we can evaluate on that test set how well we're doing on new data. It can be a little bit challenging though, because sometimes those data sets are so curated that they give us an inflated sense of how well they'll work in the wild. And so in the wild, the issue is that the data has a slightly different distribution than the distribution underlying our curated data. And we need to make sure that our methods are robust to that. So for instance, if I train my autonomous vehicle to do really well in Flagstaff, Arizona, that tells me nothing about how it's going to work in Chicago. And so we need to figure out how to make sure that we can train these systems in safe, maybe dry environments, but then figure out how to exploit that and ensure that it's going to work well, generalize well in new settings.
Okay, that's great. That's very helpful. And continuing in that same vein, can you give me some examples of how machine learning and different AI algorithms are really being applied in real world scenarios? And especially, are there some examples where it's being used in research?
Yes, it's ubiquitous. So one area where I've been doing a lot of work is in science and engineering settings. So scientists at UChicago are using AI in all different kinds of exciting ways. I have one colleague who's trying to design microbial communities that can break down plastics or that can improve gut microbiomes that are kind of out of whack. And figuring out what's the right composition of this microbial community would require just trillions of tests if it weren't for the ability of AI to help us predict which communities are good. I've got another colleague in physics who's coming up with new equations of biophysics, where he's using AI to actually learn what these equations might be from data. Another colleague in geophysics is trying to figure out how to take climate simulations, which typically have to run on supercomputers and cost millions of dollars, make them run on our laptops. And this is super important to our friends in economics who want to be able to say, how do we do economic planning in the face of climate change? This has been really hard when we can't do many computer simulations because they're so expensive. But because of AI, we just have a whole new world opened up in front of us. We also see it outside the context of science and engineering. I have a number of colleagues who are interested in societal impacts. So people are interested in establishing AI safeguards, making sure that these methods aren't being misused. And when we do this, we don't want to, have someone develop laws in isolation without understanding the technical aspects of it, because we run the very real risk that the laws will be vacuous. And we've seen this actually happen in privacy law, where the legal language corresponded to technically unenforceable and not very helpful privacy mechanisms. And this is something that we really want to avoid with AI, and people at UChicago are working actively on. We also see people using it in the context of medicine, trying to make better healthcare decisions. And even in the social sciences, we've got people thinking about how do we learn what makes a team especially functional. Can we take all of the data we have on teams, like for scientific collaborations, and figure out how to make better teams moving forward? Because we've all been on failed teams.
That is really fascinating, and something I would never have thought of.
Yeah, I mean, just the amount of creativity is phenomenal. And, I think creativity actually is another great point. We've got amazing work being done in the humanities. And I think, when we see some of the stuff that is occurring with creative material being co-opted by AI systems, there is some fear, right, about, how our creatives going to be operating in the future. This is a real concern that UChicago scholars are thinking very seriously about. In parallel, at the same time, there's a question of whether we can use AI to fuel creativity, to introduce new modes of creative work that I think is also very exciting.
So I think that's a good place for us to wrap up. If there are students, faculty, staff who are really interested in learning more about this and diving deeper into AI and machine learning, do you have any advice for them?
Well, first of all, the internet's an awesome resource. There's a number of amazing tutorials out there. And many of my colleagues and I put our course materials and videos online. But I would also say that it's important to have a very broad view about what makes a good AI scholar or user. it's not just about computer programming. That's important, but we also need to understand statistics, like we talked about, and some of the underlying mathematics. But we also need the kind of broad education that we give to our students here at UChicago. As we talk about using these systems in really critical settings, like deciding who's going to get a loan or in healthcare, we have to understand some of the past things that have happened in this country that have led to potentially biased data sets or sources of unfairness, and think about how that could be reflected by or even amplified by AI methods. So without understanding that and just focusing on the technical aspects of AI development, we run the risk of exacerbating past harms. And so I think, having this very broad perspective about what is necessary for making good AI tools is really going to be impactful.
That's great. Really appreciate your time today. Rebecca Willett, thank you for joining us.
My pleasure, Kevin. Thank you so much.
And thank you for joining us for this segment of our video series on generative AI. I'm Kevin Boyd, the CIO at the University of Chicago, and I hope you'll join us for more of the segments to come. Thank you.